This conference will now be recorded.
Okay, so welcome everyone. Today we have Masic Lipinski. He graduated from the University of Warsaw in electrical and computer engineering, and he's been working in CERN, and he's specialized in control and timing for accelerators. He's a co-author of the White Rabbit, which is an extension of the PTP IEEE 1588, which provides sub-nanosecond synchronization, and one of the key contributors to the 2019 revision of the IEEE 1588 standard. He is a co-chair of the new features submissions subcommittee submissions in the P1588 working group, keeping IEEE 1588 standard up to date with new demands from the industry. Today's talk is again about White Rabbit, and we are pleased to have you here. So without further ado, Message, the floor is yours. Oh, before go further, next, like in 2 weeks, basically, we have the folks from Red Hat, and they will talk basically about like the implementation of 1588 in Red Hat, and also like we want to like have a little bit more discussions as well about various implementations on Linux and so on. Anything else, Elad, you want to add to that? That's it. That should be like great. Okay, so
great. Thank you.
Awesome. So without further ado, Masic, the floor is yours.
Okay, thanks a lot. Thanks for inviting me. I hope you can all see my screen and hear me well. Shout if you cannot.
No, we have you.
Perfect. So my name is Maciej Lipiński, and I work at the European Organization for Nuclear Research in a team of people working on generic electronics design and low-level software, which is used in controls of accelerators. So in this team, we have developed a number of generic solutions to control accelerators, among them White Rabbit. And today I will be speaking exactly about White Rabbit, which is an accurate time and frequency, which allows for accurate time and frequency transfer over Ethernet networks. So the presentation will start with some introduction to just give you a focus on where we are. And then I will go more into details of the technology. I will speak about a bit about the equipment, White Rabbit equipment, and the applications of White Rabbit and standardization. And I will summarize in less than an hour. So what is White Rabbit? White Rabbit is the name of a project and a technology, and which was initiated by CERN and GSI, which is another accelerator in Germany, to provide the next generation control and timing network for accelerators. It was purposely based on well-established standards, and those are Ethernet bridge local area networks, which we use every day, either at work or maybe after work at home if somebody still does LAN parties. So basically Ethernet networks and precision time protocol, which I'm sure you are aware what it is, but in principle it's a protocol used in industry to synchronize sensor actuators, machines in factories, in power plants and telecommunication, many other places. So in principle, a White Rabbit network is an Ethernet network to which you can connect any PC, your laptop, you can use it for playing games. However, Ethernet itself and PTP is not enough to control accelerators. Therefore, for White Rabbit, we extended the standards to provide two essential things. One is sub-nanosecond synchronization, and the other is deterministic data transfer. So by sub-nanosecond synchronization, we mean that all the devices in the network, so the switches and the end nodes, which are White Rabbit capable, are synchronized. So we show the same time, which is represented for us, for example, by a pulse per second output, show the same time to within 1 nanosecond. Now, deterministic data transfer means that if we are sending control data from a control device to all the to devices to control them, we can precisely know what is the upper bound latency through the network, and this is guaranteed. by design of the network and of the wide gigabit devices. So today I will focus on the synchronization. Then the initial specs of White Rabbit were to have links of up to 10 kilometers and a network of around 2,000 nodes. Those has been already exceeded. And importantly, White Rabbit is open source and commercially available. And I will say a bit more about this later. So the number of applications of White Rabbit has exceeded any expectations that we had 10, 11 years ago when we started the project. And those include, of course, the initial ones, which is controlling accelerators at CERN and GSI, but also synchronization in cosmic ray detectors like the one in Tibet in China, and cubic kilometer neutrino detector at the bed of the Mediterranean Sea, or German Stock Exchange. So White Rabbit is also used at German Stock Exchange. I will say a bit more about this later. In national time laboratories, for example, the one in Finland has the longest White Rabbit link of almost 1,000 kilometers. But White Rabbit is used also in a number of other national time laboratories around the world. And also White Rabbit was evaluated by a European Space Agency for distribution of time. So those are just few of applications, and we are trying to track them on this web page. And I will speak also a bit more about applications later. So how does White Rabbit work? What are the cores of the technology? So as I said, White Rabbit is based on Ethernet, gigabit Ethernet, in particular gigabit Ethernet over fiber. This is what we use, and precision time protocol. So for the gigabit Ethernet, and precision time protocol, and then this in terms of time is extended with a number of enhancements, in particular layer 1 synchronization, a fancy way of measuring the phase using digital dual mixer time difference, and link delay model. So let me now go through each of these elements. So I'm again sure that you know what gigabit Ethernet local area network is. Just to set the ground, we are speaking about low layer 2 Ethernet switches, which White Rabbit switches are, that forward the traffic between ports based on MAC addresses. So it's not routing over IP. Now for precision time protocol, it is a frame-based synchronization protocol, and which synchronizes devices based on exchange of packages or Ethernet frames. So in very brief, because you all know it, if we want to synchronize two devices, a slave to a master over a link, those two devices exchange packages. So the time transmitter, so the master, sends an Ethernet frame, and the transmission of this frame is time-stamped with the time of the master. When the same frame is received on the slave, this is also time-stamped with the time of the slave. This is repeated again in the other direction, and the T1 and T2 are transferred to the slave. In the end, the slave, which is to be synchronized with the master, ends up with 4 timestamps, and with some very simple map that you can see, you can estimate the delay over the medium, so the delay over the network link, and then correct the offset from master of the slave such that this corresponds to the time of the slave corresponds to the time of the master. And this is basics of the precision time protocol. The same mechanism is repeated on each link in a hierarchical way, and in this way we have synchronization in the entire network. Now this solution, which is basically a default way of synchronization in PTP, has some shortcomings that White Rabbit addresses, and those are that each of the devices in a typical PTP network works with a free-running oscillator, and that means that the time of the device drifts while the measurement is being done and between the measurements. So while we are exchanging the messages, and between one exchange and the other, the time will drift, causing inaccuracy and jitter. Another problem is that if we want to, the better synchronization we want, the more often we want to exchange these messages, because we want to compensate for this drift. So then this also can contribute to the bandwidth in the extreme cases. What is more, the medium is assumed to be symmetric, which is almost always not true. And the timestamp resolution is usually the resolution of the internal clock of the system. Let's say for 1 gigabit Ethernet, it would be 125 megahertz clock. So those are some shortcomings that wide gigabit addresses with its extensions. And the first one is the layer 1 synchronization, which in principle is very similar to the sync E that you might know. In this schema, the timing master, the grandmaster, which is usually hooked to some good source of time like a cesium clock or a GPS discipline oscillator, it uses this time, this frequency, and this very good frequency to encode the data that it transmits. So it transmits with data the clock. The clock then is recovered by the downstream devices and used for its operation, which means also that the same clock is used to transmit the data downstream and then recovered again. So we repeat this. Thanks to that, without sending any PTP information, we have the same very good frequency in all the devices in the network, which compensates for the drift. So basically, we don't have anymore the drift of one clock with respect to the other while we are measuring and between the PTP measurements. What is more, the same clock on this downstream device is used to send the data back. So what we end up having is a frequency loopback. So this device is sending a frequency, this one is recovering, is sending back, and this guy is receiving. So the timing master, I hope you can see my mouse. The system timing master is receiving its own frequency after this loopback. And this is very useful because we can now cast the problem of timestamping into phase detection, which can be done much more precisely than latching just the counter, which is incremented at every 8 nanoseconds. So then what we do, we measure the phase between this transmitted clock and the received clock, and we do it using digital dual mixer time difference. Okay, you can use any phase detection techniques. You can use any phase detection techniques, but this one is very neat if you are implementing your systems in FPGA because it's very resource friendly. It requires very few resources and it scales well, so you can have many channels using very few resources, and it provides very good resolution and very good precision of phase detection. We are speaking, in our case, the theoretical resolution is 0.97 picoseconds, but we are getting to few picoseconds precision actually in the measurements. So how does this work? If you have two input clock frequencies, clock signals which are of the same frequency and between which we want to measure the phase, we first produce another frequency which is slightly offset from the one that we are measuring. And by slight offset, I mean that if, for example, we are using 62.5 megahertz, the offset clock is 62.496185 megahertz, so very close. Then we feed the two frequencies, the two clock signals that we want to measure the phase between into flip-flops, and we gate those flip-flops with the offset frequency. This creates a sweeping effect where, without going into details, what we have is at the output of these flip-flops, we have two clock signals with much lower frequency, but where the phase relation is preserved, but is much larger now. So now we can actually measure the phase offset between those two clocks by just counting the ticks of the fast clock and then down converting to back to the original frequency. There are papers on this, so the main thing is that we can easily measure the phase very precisely, but basically zooming in the clock signals and counting the phase offset between them, and then down converting this phase offset to the fast clock. Now, having this precise phase measurement, we can enhance the timestamps to have them very precise. So with the two previous steps, what we get is very precise measurement of the round trip. So we have very precise timestamps on the master and on the slave, and therefore we can measure very precisely the round trip over the medium. Now, this medium is imperfect and it is surely asymmetric. So to actually achieve synchronization, we need to correct for those asymmetries, and those come from many sources. For example, the FPGA, the delays inside the FPGA, the PCB traces, the SFPs, conversion from electrical to optical, the chromatic dispersion of the fiber itself. In this case, it is worth noting and important that in White Rabbit, we are using one fiber for two-way communication using different wavelengths. And this actually prevents us from having another source of inaccuracy, which would be different lengths of the fiber. So by using one fiber, we at least know that it is the same length in one in the other direction, and we know which wavelengths we are using in one and the other direction. So we know what is the relation between the delays in two directions on the fiber. So this is quite an important piece of information. Now, in White Rabbit, we figure out some very simplistic link delay model of the link, which divides the asymmetries or the delays in the link into two categories in principle. Fixed delays, those are the ones that would, in a given temperature, not change over the lifetime of the device, module, or the aging and other effects. But in principle, it is stable. And the variable delay, which is the one on the fiber. And this is changing because you change the length of the fiber, because the temperature of the fiber changes. So those we divide them into those two delays. It's very simplified, but it works very well. And now the fixed delays, we calibrate. We have a special procedure to calibrate it, and then we configure it into device. The variable delays, we know the relation between the delay in one direction and in the other, because we are using one medium and two wavelengths. So we can actually figure out something we call the alpha parameter, which represents what is the relation between those two delays. And this allows us to calculate the asymmetry of the medium. So with all this information, we enhance a bit the simple formula of the PTP to include the information about the fixed delays and the relation on of the delays on the medium to get a very precise delay from the master to the slave. This we use to calculate the offset from master, and then we end up with very good synchronization. And how good it is? We made a very simple experiment in which we connected a White Rabbit switch acting as a grandmaster to a cesium clock, and then through 5 kilometers of fiber we connected another switch, and then another. All of this was sitting on one desk, so we could compare the pulse per second outputs on an oscilloscope. We then took our favorite toy, which is the hot air gun, and we simulated the changing environmental conditions by heating up the fiber, and we measured the accuracy and precision of synchronization by looking at the pulse per second outputs. So this figure, which we have been showing since 2011, shows that the first slave switch, so the boundary clock, if you want to use precise terminology, was off from the master by 160 picoseconds. So this is what we call the accuracy, and then the standard deviation of this was 5 picoseconds. Then the other one went the other direction, so was closer actually to the master, and then the other was here. So even if we are not lucky and it was going into one direction, we are still within 1 nanosecond. And the accuracy per link is around 150 picoseconds, with precision below 10 picoseconds, precision defined as standard deviation. So this has been working since 2011, as you can see. Of course, we are not we are working to improve this performance, so we are not lazy over these 10 years. And the current state of art of we can achieve and what we are actually using as we speak in the accelerators is that we can achieve accuracy of below 10 picoseconds and jitter of below 100 femtoseconds RMS from 10 hertz to 10 megahertz. So it's quite a bit of improvements that we have made. This is state of art. So you need to, you will not achieve it with standard wide rabbit equipment, but it is achievable and used in current applications. So what is the equipment used in wide rabbit? Wide rabbit is an internet network, so we use switches and end nodes, which we call wide rabbit nodes. And of course, you can connect any standard equipment to it. So the switch is a central element of any wide rabbit network, and our current one that we are using has 18 gigabit Ethernet ports, which all support wide rabbit features. We use by default optical transceivers up to 10 kilometers. However, people use more powerful lasers, a single mode fiber, and this switch is fully open source, commercially available from 4 companies. Now we are working on a new switch, version 4, which would have up to 24 ports and would support 1 and 10 gigabit Ethernet, all with wide rabbit features, and it would have support for redundancy, like redundant and cost-swappable power supplies and fans, expansion board, so that you can add new features without redesigning the hardware, and it's fully open as well. As for the end nodes, those depend on the application, and we have a variety of different end nodes with different form factor, PCI, VME, and so on. And okay, for our applications, we use the concept of a carrier board and an FMC board that you plug and you have some functionality. But this is all, I mean, it's a generic. There are people producing also other form factors and other solutions. Now, what is important is that all these boards have an FPGA that run wide rabbit node IP core implemented in VHDL and system Verilog, which provides all the wide rabbit stack. So it has it is an HDL IP core that internally has a microprocessor that runs the wide rabbit PTP stack and provides wide rabbit time. It's a fancy Ethernet NIC, if you want to call it. And this one is basically instantiated in any wide rabbit node, and then usually our clients are implementing some functionality to make it work for their particular application. So we have different. There's a number of many applications. But the point is that when we think about wide rabbit node, we think more about the IP core that is instantiated in a variety of hardwares. And yes, wide rabbit is open and commercially available in 2 senses. One is that most of the open source designs that we have are commercially available, so you can buy them or you can produce them yourself. So for example, the wide rabbit switch is essentially the same hardware in different colors, produced by 4 different companies. We have also nodes produced by many companies. So all the first 2 shelves are all hardware which are open source and commercially available. But we have there's also hardware which is commercial and proprietary, meaning that this is not open, still it supports wide rabbit. Now, if it comes to applications, as I said, the number of wide rabbit applications has exceeded our expectations, and those applications can be divided into a number of categories, let's say. So I will go through each of the categories, giving 1 or 2 examples, but there are more. So first is pure time and frequency transfer, meaning that you transfer 10 megahertz clock and 1 PPS from one location to the other. And this, of course, is interesting not to so many people, but surely to national time laboratories. And there is around 5 national time laboratories in 5 different countries that are using wide rabbit or evaluating wide rabbit. This application is also looked at by Deutsche Telekom. So you can see here a slide that I have stolen with permission from Helmut Imlau from Deutsche Telekom showing the possible future design architecture of telecommunication network in Deutsche Telekom, which is the golden standard for any telecommunication network. And in this figure, the white rabbit, or now high accuracy, as I would say in a few slides, is considered for the core of the network. So then it's purely just transmitting time. Now the next type of application is time-based control, which is actually something that is very useful in accelerators. So imagine you have a huge accelerator which has 27 kilometers in circumference, and you want to trigger some action in different places of the accelerator at the very precise moment. And the beam in the accelerator is running at the speed of light, and the signal that you would be transmitting to trigger this action is running at 2/3 of the speed of light. So you cannot simply just say that this should happen and send this information to different locations, because the latency of the transmission will make such that this will happen at different times, and this could be even different by a few microseconds. So what we do at CERN and many other accelerators, we trigger actions. So we, in principle, send control messages in advance to different locations. So they will arrive with different jitter, because Ethernet network introduces jitter. But since white rabbit is deterministic, we know what is the maximum latency, so we know how much in advance we have to send it. And then once it arrives, basically the information waits until the scheduled time, and then it's executed. So this is how white rabbit is used to control accelerators. And this, for example, is now working in GSI. So GSI is an accelerator in Germany which uses white rabbit to be controlled. I mean, for controls, they need 1 to 5 nanoseconds accuracy, 10 picosecond precision, so it's perfect. In 2008, they had 130 nodes and 32 switches, but now they are more approaching to a huge network of 2,000 nodes and 300 switches in 5 layers, as they are approaching a final deployment of the network. Now, the next application, type of application is precise timestamping. And we can have two types of timestamping. One is timestamping of events. This is called time to digital convert. This is done by time to digital converters, where basically we timestamp the point in time at which the voltage level goes over threshold. The other type of timestamping is digitizing, done by digitizer, where you basically assign a voltage value to time, and so you can recreate, for example, the waveform. Now, this is actually the most popular application on white rabbit in the world. It is used, for example, to measure time of flight, to do the time of flight measurement. So, for example, measure the time of flight of neutrinos. So the first application of white rabbit was the second run on the infamous CERN neutrino 2 Sasso experiment, where in the first run it was hinted that maybe the speed of neutrinos is faster than the speed of light, but then we use white rabbit to figure out that it's not true. So this was sad, but okay. So that was the first application of white rabbit. The timestamping is also used to, for example, figure out the type of particle. So we have this protodune experiment where we hit a target with particles, and then when they leave, they have different momentum, so different speed. So by measuring the time of flight over a given distance, you can figure out what is the type of particle. Another application, cosmic rays and neutrino detectors, as I said. So in this particular case, what is happening is that there are spatially distributed sensors that detect cosmic rays coming from the space, and in arrays, let's say in Tibet, it's 1 square kilometer, and so based on the measurement in different places, you can figure out the trajectory of the cosmic ray, so basically the origin where it came from. So one example is the lasso experiment. Another one is this KM3net at the bed of Mediterranean Sea, where The same applies to detection of neutrinos using the Cherenkov light. The Tunka experiment in Siberia is also using White Rabbit. And finally, timestamping is also used at the Deutsche German Stock Exchange to timestamp the high-frequency trading traffic. And this is done to monitor whether there are any suspicious behaviors or any patterns in the trade, because this is done at very high speeds with low nanosecond level latencies. So basically the Deutsche Börse is monitoring this traffic to make sure that this is just. Another type of application going further is based on the previous one. So let's say we have timestamped the input trigger in one of the nodes. What we can do, we can take this timestamp, this value, and send it over White Rabbit network to many other nodes which are far away, and reproduce this trigger with fixed latency in all the nodes, regardless of the distance. This gives us a delayed pulse with very precise delay. Now, this is a very simple concept, but it's very useful. We've been using it for now 5 years at LHC in something we called LHC instabilities. So in the LHC, we have observed some instabilities of the beam that develop over time, and it was not known fully why they developed, so they had to be studied. So what it did, we distributed over the tunnel a number of observation boxes, which are basically digitizers that are sampling the parameters of the beam and digitizing them and storing them in RAM buffers. So if any of these observation boxes detects that something might go wrong, it sends a trigger to all the others to stop the acquisition. This trigger is delayed, so all the other boxes stop the acquisition at the very same moment. And this allows us to use standard digitizers without White Rabbit support to coherently see what happened in the accelerator. So what we are doing, we are basically rewinding the acquisition, which stopped at the very same moment, to see what happened coherently in the entire accelerator. So this will be further extended to use in our gigantic oscilloscope, which has many thousands of channels and spans all over the accelerators to distribute triggers. Now, a next type of application is something similar to the trigger distribution, but in terms of data that might be useful for maybe for data centers. So what we are doing fixed latency data transfer. Imagine you have two remote White Rabbit nodes, so devices, and you want to transfer data from one to the other with fixed latency to within a nanosecond. So what can be done? What is done actually, that we are when the guy on the left side wants to send data, this moment in time is timestamped, and we send this timestamp along the data in the Ethernet frame to the other guy. Now there can be a jitter on the transmission. However, we delay the exposure of the data, so basically buffer a bit the data to expose the data to the other user on the other side with fixed latency. So it is as simple as it sounds, but it is very powerful. Now, why would you like to do it? Well, it is very useful if you have distributed feedback systems. So imagine that this guy is controlling, this guy is measuring, this guy is controlling, and you have a feedback loop, which, if you know a bit of control theory, you know that you assume fixed frequency and fixed delay in your model of PI controller or whatever type of controller you are using. And this is precisely how we are using it at CERN. So at CERN, in most of the accelerators, in all of the accelerators, the acceleration of the beam needs to be synchronized with the increase of the magnetic field in the bending magnets, because the more you accelerate, the more energy has the beam and the more magnetic field you need to use to bend it. Now in most of the accelerators, how it works is that we measure the magnetic field from a reference magnet, and we send this information in real time to the people which are responsible for the supply, so for the to the power converters, and they in real time correct the current to achieve the intended magnetic field. So you can imagine that those two can be meters or kilometers apart. And also another thing is that we send this information also sent to the radio frequency cavities, which accelerate the beam with a frequency which is appropriate to the current bending magnetic force. So in principle, you have here a closed loop where we need to correct the current to have the intended magnetic field, and the open loop where the RF cavities are following the changing magnetic field. Now the last and the most advanced application of White Rabbit is to transfer radio frequency over White Rabbit. And so the goal is to basically transfer a signal, for example, a sine wave, from one place over White Rabbit network to many other places, and in such a way that the output of the sine wave is phase aligned in all the places. So it would be a delayed copy of the input, but perfectly phase aligned with all the receivers. And how do we do this? We are using something called direct digital synthesis. So what we do, we take the White Rabbit reference frequency and time, and we use it to synthesize a signal, RF signal, using this DDS convention, which basically, very simplistically, is a lookup table that you play and outputs to digital to analog converter, which in turn outputs a signal. So what we do, we synthesize a signal and we lock it to the input signal that we want to transmit. So we detect the phase between those. Then we have a PI controller which makes sure that the DDS is following the signal. Now the control words to this DDS are basically a digital representation of the analog signal. And this digital representation we pack into Ethernet frames and send over White Rabbit network, and then recreate on the other side with a controllable adjustable delay. And that's it. So this is basically how we can transfer almost arbitrary frequency from one point to many points in the accelerator. And this is used in two accelerators currently, and being or even more, which I'm not aware of, because many accelerators are interested. One is the ESRF in France, and then as we speak, we are now deploying the system at CERN. And at CERN, for this particular system, we need the precision of below 100 femtosecond, the jitter, and the reproducibility after reboots of 10 picoseconds of the phase alignment between different outputs. And this is used to control radio frequency cavities that accelerate the beam. So this is some kind of a spectrum of different applications with some examples. Now, White Rabbit, as you might have heard, has been included into the standard, into the IEEE 1588 standard. So maybe you are aware that the IEEE standards are periodically reviewed. And when the IEEE 1588, also known as Precision Time Protocol, PTP, was starting to be reviewed, the IEEE working group, the P1588 working group, thought that White Rabbit improvements are quite interesting, so they agreed and decided to insource these changes to the standard, and this was basically marked with this few words saying that the 1588 will provide support for synchronization to better than 1 nanosecond. So how it was executed actually over roughly 6 years is that the working group that works on the 1588 standard was divided into 5 subcommittees, namely management, security, architecture, and maintenance, and the third one, which was the high accuracy subcommittee, which focused on White Rabbit. It included experts from industry and academia like Cisco, NIST, and Xilinx, Deutsche Telekom, who all looked at White Rabbit specification and how White Rabbit works, and worked on translating it into the standard language. So as a result, White Rabbit was divided into self-contained parts that could be useful by themselves, and all together they would create White Rabbit. So those were defined as optional features, and then a third default P2P profile was added, which is called high accuracy, which basically effectively allows to implement White Rabbit and provide its performance. So this standard was approved in 2019 and is now in force. Now, how White Rabbit was incorporated into the standard? Okay, the details you can find under the link, and just in short, first of all, few things in the core of the standard have to be added, like definitions to make things work. Then three optional features, high accuracy optional features, were defined. One to calculate the delay asymmetry, one to introduce the configurable correction of timestamps, and one to allow the layer 1 synchronization. And also an annex was added to explain how to calibrate stuff. So those are the high accuracy specific optional features. Then a number of more generic optional features were defined and added, which are useful also, which are known to be useful currently also for other applications. And those include some tweaks to BMCA, base master clock algorithm, which namely are mechanism for external port configuration and master-only mode for the ports. Now, finally, a third default profile was added, which is the high accuracy request response default profile, which mandates all of the new features to be implemented and requires that the high accuracy specific features are active by default, enabled, and the other ones are inactive but accessible. So they should be they have to be implemented and they can be used. And now another thing that was added was annex, which explains basically how to implement the new profile such that sub-nanosecond accuracy of synchronization is achieved. So just to summarize, and I think I'm within the time, White Rabbit is an Ethernet-based synchronization solution that out of the box achieve without any problems sub-nanosecond accuracy and 10 picosecond precision. And then the current state of art is that we can achieve sub 10 picoseconds accuracy and sub 120 second precision. It is open with commercial support, meaning that you can either buy open source White Rabbit devices and then also have support from the companies, or you can go to our web pages and produce those devices yourself and modify as you please. It is standard-based and standard extending, as you have seen, because it was included in the revised 1588. And in general, it's a versatile solution for general control and data acquisition problems that are faced by accelerators and other scientific organizations, and also outside the industry more and more at these levels of accuracy. And it is a showcase of technology transfer from science, in particular from CERN, to the outside world in the technology and the industry. And that would conclude my presentation. Thank you for attention, and I will be happy to answer any questions. If you are still there listening.
Very good, very good. I have a quick question, actually, if I may. So, so the femtosecond precision, picosecond precision sounds very interesting. What is the source of time, actually? Do you care about like absolute time or only about the relative time to the nodes? Because like GNSS solutions cannot provide such precision if you were talking about true time.
True, it is correct. In our applications, we care about the relative time in our complex. So we are hooked to GPS, and this is mostly for this stability of frequency and to be traceable for, let's say, post-mortem analysis when we need to coordinate timestamps from NTP, from White Rabbit, and so on. But for our applications, the most important is the synchronization between the White Rabbit nodes, because femtosecond accuracy of UTC or TAI is basically impossible.
I probably have another question then.
Okay, no problem.
While we have a pause about the so-called grandmasters, right? So if you use them as a source of time, do you also have proprietary or basically White Rabbit enabled hardware on those devices?
Sorry, I was laughing because I see Sven with his T-shirt. Yeah, I see we have fans. Okay, to answer your question, so the Grandmaster in our case is the White Rabbit switch, which is open source, and then it is connected to a GPS disciplined oscillator, which can be anything that gives you 10 megahertz and PPS, or a cesium clock if you. So basically, the Grandmaster itself, the PTP Grandmaster, is open source because it's White Rabbit. But the source to this Grandmaster is something that is in 100% of cases proprietary. And we would be happy to be able to hook to a source of time which is open, or to have the GNSS disciplined oscillator which is open and speaks White Rabbit on one of the ports.
So Masih, do you see like an application for the time card? Let's say to put the time card on that node and then basically get it from there?
Well, of course, that's basically another source of time that we could use if it was available. We would be happy to test it, of course, yes.
Wonderful. So we'll send you one then.
Okay.
So I don't know if Dotan is here. Like I think Dotan was going to ask something, or maybe I can ask like for the synchronization, like what's the main difference between like the method that you currently have and let's say SyncE? It's pretty much the same, isn't it?
Yes, it's just that we cannot call it SyncE because we are not compliant with all the metrics that SyncE has in this. So I think the gain picking is a bit different. So in principle, the rules are the same, just that some of the knobs and parameters are not following what is in SyncE specification. Plus, we don't have currently any holdover, so we cannot basically fulfill this specification. But that's why we are not calling it SyncE, because it would be not proper. But it's very similar. It's just almost the same.
Is holdover even a thing? Is it a necessary thing in your case?
Yes, holdover is something that would be useful, although it's not that trivial if you want to maintain sub-nanosecond accuracy of synchronization, because you will very soon go out of this range. However, it can be useful out of two reasons. One, even if you, let's say, if you want to swap between, let's say you have redundancy, so you have redundant ports. It takes time to swap between redundant ports, and in this time you would like to use holdover, and it is feasible to maintain quite good accuracy with not so expensive oscillator during rearrangement of a fast rearrangement of network. And for the second reason is that what we said, we are caring only about the absolute time. So let's say if a grandmaster is drifting on holdover, we don't care. because the entire network is drifting and it's still some nanosecond accuracy. So in these cases, yes, if we have if a switch somewhere in the middle of our network goes into holdover mode, this is not so ideal because then we can lose part of the nodes, and we can, in the best case scenario, we will dump the beam safely, and in a less nice scenario, we'll drill a hole in accelerator. So.
So one thing I was thinking about is like, let's say, and I don't think synchronization is ever important. It's more like the synchronization. So the holdover, the performance of the holdover is more about the synchronization, I'll say, in your case, because even though your network goes down, let's say the grandmaster, whatever you call it, the main switch, when then your experiment needs to be basically based on a reference because time is the parameter in it. That's why I was more thinking like, perhaps you have a cesium clock that is like holding the whole thing for you.
Well, in our particular case, we are based on rubidium, but yes, you are true that for some time synchronization is enough. But then over time, when you take into account the temperature effects, then you need to correct for this. So short term, yes, synchronization okay, but long term, you always need to correct.
One question: how fast can you go back from an unsynchronized state to a synchronized state again? I mean, if you're following all that in a sub-nanosecond range, I guess you also want to slowly adjust again.
You are correct. So because also you don't want to, because you are adjusting but by modifying the frequency. So if you go too fast, basically your frequency will go off too much. Currently in deployment and release, we don't have this implemented. So if you are down, basically you just stop everything. So this is not in operations yet. We haven't yet implemented it in a way that we could use it in operations.
Okay.
This is the answer. We had some experimental implementation, and I don't know what was the limit. I don't remember the limit, so I cannot. I don't remember. I cannot answer this question. I can send you by email later.
But probably slow.
Yeah, it has to be. It has to be slow because otherwise you will basically have false frequency for some time, which is bad on its own. So it needs to be very slow. Yes.
Thanks.
Here is one that's a little bit more technical. For your synchronization, you use GPS. So let's say the accuracy of the synchronization, I'm assuming like it's like in range of tens of picosecond or something. So how do you get that from your GPS while the GPS is not giving you, like I make different methods like averaging, whatever. Like I want to see like which method you guys use to basically extract now the frequency standard basically from your GNSS.
No, wait, we are using rubidium, well, GPS disciplined oscillator, which is rubidium clock. This is out of the shelf solution.
Sure.
So then rubidium is quite stable short term, and GPS is stable long term. So on our end, in the WideRabbit devices, we are not doing anything sophisticated. We are just taking 10 megahertz and 1 PPS, and that's it. We are using ultra low jitter devices that provide a very high quality of 10 megahertz clock, and that's enough for us.
So you don't go after, let's say, steering your rubidium clock to have it now. Okay.
No, we use as it, I mean, out of the box 10 megahertz.
Use it basically based on whatever it's calibrated for.
Yes, exactly.
Interesting.
Now, hold on. So you say you're using the solution off the shelf. So do you know if this solution is actually steering the atomic clock itself, or you think it's just internal logic which it gets disciplined and uses 10 megahertz as a reference?
Well, I don't know. I guess that you steer the clock, but okay, this is a black box solution, and I don't know exactly. We just measure that it is sufficient for us, and I doubt that you could actually do it with ultra low jitter by generating by not steering directly somehow the oscillator. But I don't know.
No, the challenge is like twofold. One is like that steering. Either you do it like with the oscillator to have like the lowest jitter and better like granularity, and like versus like let's say doing it in digital, you get it and then you basically tweak the DPS or something. And the second, again, twofold, right? The second problem is basically now you need to extract it from your GNSS signal, that perhaps with a prolonged measurement, you can basically look at like lower accuracy. It's also higher accuracy, because the GNSS on its own, it's great in terms of stability, but it's not good, let's say, if you just want to look for the consecutive, let's say, pulses to do the synchronization. And that is like,
By consecutive pulses, you mean PPS output?
yeah.
But the PPS output is basically aligned with 10 megahertz. So if the 10 megahertz is stable, in principle, the PPS
comes from, again, if you just look at the PPS pulse, the consecutive PPS pulses from the GPS, you will have them like basically jumping around 1200 seconds.
Yes, sure. I'm looking now at the output of the box, which is already averaged. For me, it's a box which takes an antenna and it has a rubidium clocking site, and it gives me 10 megahertz in PPS. Yes, that's it.
We have the box opened.
yeah, I know. So for us, this is enough, let's say, because what we need is a very good low jitter
Like
source
even
of
if
frequency.
you have, let's say, for example, a TCX or coupled GPS that gives you now the pulse that comes out, right? You still, let's say, if you're taking that and you want to let's say steer an atomic clock, you have to up that, like, let's say, computationally to a point that now it will make sense, let's say, when you want to steer picosecond. So what we're thinking about is like basically we want to do like prolonged things. It's basically, it's like you're trying to measure something, you extend the measurement, you extend the error, you amplify the error to basically.
Sure. You are doing averaging I think this is what is the name for it.
Exactly.
Which is basically what is done routinely, especially in time laboratories when they are basically averaging the time.
Yeah. Averaging without the averaging part without dividing, so it's just accumulation.
Yeah.
Okay, any other question?
Is it possible in the future we can have some comparison or to a smaller circle for those who working on connectivity project to focus on comparing 1588 with the Sync-key? Because these are two standard for those who have a less experience or exposure to the history of 1588. We might just loosely interchangeable when we discuss it, but sounds like this topic is something that will have a lot of value for the connectivity team. Do you think it's possible to call another meeting just to focus on the comparison? Is that possible? Of course, we cannot pay you money, that's for sure.
We'll see. I don't know, Masic, would you be interested to have like another, let's say, more technical, let's say, discussion focused more on what Arthur was asking, like more for connectivity applications?
Well,
telecom.
Yes. I would prefer if some expert in Sync-E does it, but to answer shortly, I don't think you want to really compare that much Sync-E and PTP, because, okay, historically, Telecom was using Sync-E, but now they are moving, then they wanted to use synchronize over Ethernet networks, so they prepared a profile that basically replaces to some extent Sync-E, but in the end, now the 5G and so on, they need time and frequency. So in the end, the Sync-E is used along with PTP. So I wouldn't say that it makes much sense to compare those two, because they are complementary or used in a complementary way now, as far as I know. And also in terms of comparison, it's more like looking at the specs, because in telecom profiles and SYNC, the specification provides what should be the performance, and companies make such that it works. So it's more like just looking at the specs and seeing what is required from SYNC and from telecom profile, which is mimicking SYNC, to know what is the performance. I'm not sure that the performance, okay, it can be a bit better, but I think how it's used in principle is just looking at the specs and knowing what should be the outcome. So that would be my short answer to the question posed. And if it comes to comparing those two, I would not qualify as such an expert to give a presentation on it.
No problem. Yeah, actually we appreciate a lot today's presentation. And yes, I think you are definitely hit the nail right on the head about the word of converging. I think that is what a lot of our connectivity projects are also adopting P2P for what we know as a split architecture for the 5G. Yes, yeah, no, don't worry. It has been a good training session today. I enjoy it very much. Thank you.
Okay, yeah. So any more questions? Calling once, calling twice. Okay, great. Okay, Masis, again, thank you very much on behalf of OCP TAP community, and wish everyone good for the rest of your day.
Thank you very much, and it was a pleasure.
Thank you, everyone.